2, 1. All right, the next topic deals with work done by a spring. This is also known as a variable force because what you get here is rather than a horizontal line between force and distance, you get something else that we're going to take a look at. Hopefully you saw the video. If not, you just stop right now and look at the video about this because this explains a lot of what I'm about to talk about here. All right, so if I were to make a graph for the relationship between the force applied and how far the spring moves, our x-axis here is going to be the distance. And normally you would think d would be distance, but in physics circles they use x for this. If you use d, it's all right, but just make sure you're aware of that when you look at textbooks later on. They don't use d like we did. And force over here, which is F, is going to be measured in distance, newtons. And the distance here is to be measured in meters. Okay, so when you take a look at the relationship here in the spring where you start at equilibrium, you pull it down, and it bounces back up, and it comes back, the expansion and contraction of the two, in theory, should be the same. Of course, friction and gravitational pull. Well, gravitational pull is not a big deal as much as it is the frictional aspect of the spring itself, rubbing against each other and slowing it down. In fact, the gravitational force is theoretically the same because you pull it down and then it's going to snap up against gravity reaches a certain point and gravity takes over, brings it back down. It's just like we were talking about throwing a ball straight up in the air and how gravity works for and against you in that scenario. So if we were to take a set of data of the amount of force you apply to the spring and the distance it stretches out, and assuming that we don't reach the point where we damage the spring, you're going to get something that looks like this. Now, this is why they call it a variable force. Because you normally expect the same amount of force is going to be pulled a certain way, but because of the makeup of the spring, it's going to snap back. It's what is called elasticity. We're going to get a right triangle out of this. Okay? Now, it turns out that the slope of this thing is our k. Remember, k we said in the strip there is the spring constant. Now, as I've always described, whenever we're dealing with a constant, whether it's ideal gas law or Arrhenius law or anything like that, the constant you get is basically, or normally, nonsense, or a bunch of variables just trying to tie all the variables together into some kind of cohesive unit. This actually has an application. If you take a look here, if you were to find the slope, this is y2 minus y1 over x2 minus x1. Well, y is force, so this is f2 minus f1, and then the distance is the x2 minus x1, and f2 minus f1, that is measured in newtons, and x2 minus x1 is measured in meters. So the label for this is going to be in newtons per meter. So anytime we work with springs, even though they're generally small, unless you're dealing with a slinky, it's going to be measured in centimeters or even millimeters, depending on how tight the spring is. You're going to have to change the meters so that you get the K value that you can compare with other K values. Meaning, we know that a slinky has somewhere between 1 and 5, and we have a regular spring that's in the neighborhood of 200, then you know that the 1 to 5, the slinky, as you well know, is very loose. It doesn't take hardly any energy at all to pull it or push it or whatever. But regular springs, you have to really work to get it apart. So the higher the number, the tighter the spring. Okay? Now, I'll also show you here that we have created here a right triangle. And the fact that this is a right triangle has another significance. Now, let's just presume that we have a rectangle. Now, if I took another triangle like this, flipped it 180 degrees and lodged it in there, we would get a rectangle of the same dimensions of this and this. Okay? And if that's the case, then that means that this is 1/2 of that. That's why right triangles, or any triangle for that matter, area is 1/2 base times height, not base times height. Because it's half a parallelogram or half a rectangle or a square or whatever it is you're dealing with. It's half of that area. So that means, now let's assume that we have this regular rectangle. Force times distance is defined as what? Work. Okay? So this area in here is the work of a variable force, so the work of the spring. And that equals to 1/2 base, which is distance, times height, which is force. Or we can simply write it as the work is equal to 1/2 F times B. Now, let's take a little variation here, because sometimes the problem we have will actually want us to break this down. Force is defined as mass times acceleration, so we can also write it as 1/2 mass times acceleration times this, the distance. Okay, so these two formulas are the same thing. It's just that this is expanded to show you more of the different ways that we can look at work. Okay, so let's take a look at some examples here. What is the spring constant for a spring that requires 55 newtons in order to stretch 25 centimeters? Okay, so let's go back over here. What did we say K was? Well, K was newtons divided by meters. Another way of saying that is K is equal to the force divided by the X. Now, the formula then can be rewritten as force equals K times X. These are variations of the same thing. So if you're solving for K, you would put K equals F over X, because you divide by X. You get K by itself. Okay, so this is the Y equals mx plus b version of this scenario. Y is the force, X is the X. How about that? And K is the slope, and there's no y-intercept, so there's no plus b. So this is our formula, and this is called the Hooke's law. So we're going to use a variation of Hooke's law, which is K equals F over S. Okay? So let's take a look at the numbers we got for this again. So we know that the force is 55 newtons, and the distance is 25 centimeters. All right, so force is 55 newtons, and the distance is 25.07 meters. All right, so the formula then for this is going to be K equals F over X. But we know that the label for this has to be newtons per meter. Well, we got newtons right here, that's 55 newtons. But this is not written in meters, so we got to change the centimeters to meters. So with centimeters on the bottom, meters on top. Meters is the larger label, centimeters 100. We divide that out, and we get 0.250 meters. Divide that out, and our answer is 220 newtons per meter. That is the rate constant or the spring constant for this. So the spring constant, 220, is about normal. It's normal. Okay, let's take a look at another scenario. What is the amount of work performed on that spring in this problem? Okay, so let's take a look at that. Now, here's our formula for this. 1/2 F times E. All right, so since that is the formula, we also have to remember that force is defined as K times D, so that's 1/2, or K times X rather. K times X, and then D. Now D can be replaced with an X. Since we're talking about X, we'll try to be consistent here. So that means the work is going to equal 1/2 kx squared. Or if you prefer the D, which is fine, I really don't have an issue with that, K times D squared. Either way is fine. So when we plug this in, we get 1/2 times the force, which we said was 220 newtons, times, the K value rather. The K value we said was, that's 220 newtons per meter. Sorry about that. Times X squared. Well, how far do we pull it? 0.250 meters, have to be meters, 1 squared. Okay? So we multiply this out, do that in some way. Okay? So 6.85 joules is what I should have done for an answer. Okay? Your assignment is page 175, problem 17 for 21. All right? Good luck.